an important role. Because if I just combine the thermal conductivities of these materials alone, it will not give me a value as low as 0.2. The reason why all 5 of these, when put together, perform even worse than the worst one is that they are not talking to each other. Is that the heat has a very difficult time jumping from one material to the other. And in fact, towards the end of the lecture yesterday, we said that there are a total of 4 contact resistances here. Current collector to anode, anode to separator, separator to cathode, cathode to current collector. And the question is, which of these resistances is the dominant resistance in this problem? Okay, so that is going to be the topic of our first lecture today. We will talk about thermal transport at the interfaces between materials inside lithium ion cells. Okay, so before I do that, I think there was somebody had asked this question about how do we measure the thermal conductivity of these materials. In the lecture yesterday, I had presented a technique for measuring the thermal conductivity of the overall cell, right? I want to briefly talk about thermal conductivity measurement at the scale of materials, and for that I will actually bring up a paper by Vivek Vishwakarma in 2014. He at that time was a PhD student in my lab, and he came to UT Arlington from IIT Ropar. He was a BTech student of Dr. Tyagi. And the point here is that the separator is a very thin material, sort of like this. What I've shown here is those paper rolls comprising the anode, cathode, separator, etc. So this is the positive, sorry, this is the negative electrode, the other one is the positive electrode, and in between is the thin separator. It sort of looks like a paper, or it looks like a thick polythene bag, sort of like that, right? And the question is, how do we measure the thermal conductivity of this body? Okay, there are several challenges in doing that. Mainly, when we were talking about the cell, or when we were talking about the cell, we said that we'll put a thermocouple on this side, put another thermocouple on the other side, and measure the heat flux, right? Now, the smallest thermocouple that you can probably buy has a bead size of 200 microns, whereas my body itself is only 50 microns thick, right? So in other words, we are here entering the realm of micro scale dimensions, where large sized bodies like a thermocouple will simply not work. So we had to come up with our own measurement technique to measure the thermal conductivity of the separator. And the way we did that was the following. I'll talk about the experiment first. So this is a good picture. The blue is the separator for which I want to measure thermal properties. Okay. In order to measure the thermal properties of the blue separator, think of a piece of paper. I want to measure the thermal conductivity of that piece of paper. What I did was, or rather Vivek, what Vivek did was that he printed a metal line, 2 metal lines on that paper. Okay, and printing of these metal lines is not that difficult, honestly. What is typically done is that you take the substrate, you put a mask on top of the substrate. So imagine if I take a aluminum sheet and make a hole in that sheet that corresponds to the shape that I want to print, right? And I place this mask on top of the substrate, okay, and put this in a metal deposition machine. Those are called, what are they called? E-beam evaporator. Titanium is deposited using E-beam evaporator. So basically there is a source of the metal, and you take an E-beam gun and you shoot on the source, which ejects the metal atoms, and they go all over, and obviously most of them will be intercepted by the mask, but some of them will pass through the hole in the mask, and the shape that you obtain on your substrate corresponds to the hole in the mask. Right? This is a common technique. This is easily done in any lab. You just need a couple of key pieces of equipment, but other than that, this is easily doable. Okay. So we deposited two metal lines. These metal lines are very thin. The thickness of these metal lines is, I think, 50 microns or so, and they are about 100 microns away from each other, and they are very long. Okay, so that if I draw a cross section, the cross section looks like this. I have two heater lines going into the plane of the paper, and then he said, okay, let me make electrical connections and let me pass a small amount of heating current of the order of microamps or milliamps. Okay, so imagine what will happen, and this entire experiment is being done in vacuum. Let me see if there is a picture of the experiment. Yeah, there is. So he does all of this on a glass slide. He suspends the separator material over two islands on the glass slide, and then he carries out his microfabrication so that in the end it looks like this. And you can see these are wires coming out to be able to pass current. Okay. He does not have a picture of the experimental setup, so let us skip that. But I want to go back to the schematic, and I want to think about what will happen as you pass heat through one of these heating lines. Clearly, the line through which you pass current will start heating up, right? So the temperature of this line will rise as a function of time. As this heat flows through the separator material, it's like a wave. After a little bit of time, that wave will reach the other line as well, correct? And the other line will also begin to heat up. If I sit there and measure the temperatures of these two lines as functions of time, then we developed a theoretical model for this problem, which basically said that T heater as a function of time should be given by this expression. And if I take the log of this, this tells me that a semi-log plot of T heater as a function of time should become a straight line, and the slope of that straight line has information about the thermal properties of the body. This is sort of like the same thing that we did with the cell, right? With the cell also we predicted that the temperature should become a straight line, and the slope and the intercept of the straight line should give us information about its thermal properties. Similarly, we are predicting here that the heater temperature, when plotted on a log scale, will become a straight line, and the slope of that straight line gives us information about the thermal properties of the body. Moreover, we also predicted that the temperature difference between the two, the heater's line and the sensor line, we predicted that the temperature difference between the two at large times should become constant, and the steady state temperature difference between the temperatures of the two lines we showed has information about the thermal conductivity of the material. So theory predicted that if I sit there and if I keep measuring the temperatures of the two lines as functions of time, then the temperature of the heater line and the temperature difference between the two lines gives us information about the thermal properties of the body. And when we ran the measurements, it turned out to be pretty close to what the theory was predicting. This is a good plot to look at. So what I'm plotting here is blue is the heater line temperature, red is the sensor line temperature, and black is the difference between the two. So you can see that both of them are rising, but after some time the temperature difference between the two becomes constant. And that constant value at large times gives us information about the thermal conductivity of the body. And also if I plot the heater temperature as a function of time, we also find that is also a straight line, and the slope of that straight line gives us information about the thermal properties of the body. Okay? This is a good example of designing your own experiment to measure thermal properties. Sometimes there are well-known techniques already available that you can mimic in the lab, like I had explained in the lecture yesterday. But if a technique is not available, if the material is too thin for me to use thermocouples and all that other stuff, then one has to design their own experimental measurement technique. Okay? Any questions on this? So I guess the long and short of it is that even the separator has a thermal conductivity of 0.5 watt per meter Kelvin. Using the paper that I had just presented, the measured value of the thermal conductivity of the separator turned out to be 0.5 watt per meter Kelvin, and it was a little surprising because the thermal conductivity of the cell itself was even lower than that of the separator. So from there we started asking ourselves, what do we need to do in order to measure the interfacial thermal resistance of this body. Okay, so let's take a simpler example. Suppose I have two bodies, A and B, that are nominally touching each other, in which case I have a resistance of the red, a resistance of the green, and in addition I also have a contact resistance. Okay, it's possible that the red is cathode, the green is the separator, and I want to find out the contact resistance between the cathode and the separator. And the question is, how do I do that? Okay, there are actually fairly sophisticated methods for taking such interfacial contact resistance measurements. For example, there is a method called time domain or frequency domain thermoreflectance. In short, called TDTR or FDTR, which people use quite commonly in order to take such measurements. This requires a fairly complicated optical infrastructure, which I'm not an expert at, So we thought of something simpler, something more engineering in nature. Okay, we said, okay, I have a problem with three resistances, correct? Our cathode, our separator, and our cathode separator at the interface. I am mainly interested in measuring or in determining this one. Yeah. Can I find out our cathode? How will I find out the thermal resistance offered by the cathode? Sorry? No, we are talking about thermal resistances here, keep in mind. Sorry, all of these resistances are thermal resistances. Okay? So in this course, unless I specify otherwise, resistance refers to thermal resistance. So remember that the thermal resistance of any body in one dimension is given by its thickness over its area and its thermal conductivity. This expression, by the way, is very similar to electrical. In the electrical world, what is the resistance given by in terms of resistivity? Rho L over A, right? Yes, rho L over A, which can also be written as L over A sigma. Rho is the resistivity, sigma is the conductivity. Folks, this expression and this expression, they are exactly the same. In the electrical world, we have electrical conductivity. In the thermal world, we have thermal conductivity. Okay, so to find out the thermal resistance of the cathode, I need to know its thickness, which I know. I need to know its area of cross section, which I know. I need to know its thermal conductivity, right? The thermal conductivity of just the material can be easily found out using the techniques, for example, that we had discussed in the last lecture. I can take my material, I can put a heat source on one side, I can have cooling water on the other side. Remember the whole experimental setup we discussed yesterday, and we can take temperature sensors. चल रहा है ना? I got a no internet message. So from here, I can use Fourier's law to measure the thermal conductivity of this material, right? So imagine I run an experiment in which I take only the cathode and measure its thermal conductivity and therefore find out R cathode. Then I run another measurement in which I take only the separator material, run this experiment only on the separator, so that I find out, so that I now know these two resistances. Okay? What should I do next? No, no, there is not a ready connection between thermal resistance and electrical resistance. Okay, remember that I have three thermal resistors in series. I have been able to find two of them by measuring the cathode and the separator alone. Now if I measure both of them together, that measurement will give me the total thermal resistance. Right? And if I know the total thermal resistance and two components of it, I can simply subtract them out to indirectly measure my contact resistance. In other words, if the total measurement turns out to be 100 and these two components are 10 and 40 respectively, then clearly the contact resistance must be 50. right? Just simple addition subtraction. So that is what we did. We said we'll measure the cathode first, we'll measure the separator next, and then we'll put them together and measure it then again, and look at what happens to the total resistance when you put them together. That was the basic idea. Alright, let me switch to the paper in which I can discuss some more details of how this was done and some of the repercussions of the results that we obtained. So this was also Vivek's work, and as you can see, this was, I mean, this was Vivek and I, simple. The first paper that I showed, just him and I, right? The second paper is a bunch of co-authors. I was talking at that time with Ravi Prashar, who's a good friend of mine, a senior from my undergraduate years, and he helped us with some of the interfacial contact resistance modeling. There were some people involved from Oak Ridge National Lab and a collaborator, Pushong Liu, from the material science department, who helped us with the electrochemical measurements, and one of his students, Ziwei. I think none of them are where they were at that time except myself. So in this paper, we started by providing a justification for why these measurements are important, okay, and then we basically made the argument that I was making on my slides, that if I want to measure the resistance between the separator and the cathode, it is basically 3 resistances in series. If I measure 2 of them separately and I measure the total, then I can just subtract them out to find out the interfacial resistance. So to do that, we designed a very simple experimental setup in which we took 2 copper blocks. Why copper? Because copper has well-known thermal conductivity, and we drilled a number of holes in the copper blocks and inserted thermocouples on both of them, the hot side and the cold side. On one end of this, on the hot side, we inserted a metal, a thin heater. So through this heater, you can barely see, we can pass current in order to heat this up from one side. Okay, and on the other side, we drilled a big hole and connected it to a water supply, a cold water supply, and basically passed cold water. Okay, we were having a lot of difficulty seeing the cold water because water was transparent, right? And one day Vivek said, okay, and the water became red. No, just kidding. We took some other red dye and put a drop of the dye to be able to see the water. Okay, and then the most important thing is that in between the hot block and the cold block, we sandwiched the material of interest, whether it is the separator or it is the cathode or it is the sandwich of the two. Okay, so for now just imagine that this is only the cathode material, right? I have heat entering this copper block from the top and heat leaving from the bottom, picked up by the cold water and taken away, right? During this time, this heat has to pass through the cathode material to jump from the top block to the bottom block, right? This is a typical temperature versus X plot based on the 15 or so thermocouples that we had. The red ones are in the top, the blue ones are in the bottom. By the way, folks, it's extremely important when we are trying to communicate technical information to others for it to look nice, clean and organized. See, I made several deliberate choices here. I chose to use red color for all the hot thermocouples. I chose to use blue color for the cold thermocouples. And my schematic is in the same color scheme as my plots are, right? My font sizes are big and easy to see and so on and so forth. And even this picture is pretty good if you print it on paper. Of course, if I zoom in, it will look grainy. But if you print it on paper, look at it at reasonable resolution, it looks pretty good. It is extremely important for all of us to not only do good work, but also communicate it well. In fact, in our lecture after lunch today, I will talk about technical communication in terms of writing and in terms of presenting. So I will share some of my experiences and a list of do's and don'ts that I have developed over the years about how to be an effective communicator in terms of writing papers, technical reports, etc., and in terms of presenting to your advisor, to your committee, to conferences and so on and so forth. Those are extremely important skills. Do good work is half the job done, present it well is the other half. So in the afternoon today, I'll share some of the things that I have myself learned over the years. Okay? Alright, so what does this give us? This tells us a few things. Firstly, the temperature distribution in each of these blocks by themselves, either the red or the blue, is very linear, right? I'm able to fit it very nicely with straight lines in both of them. However, interestingly, there is a large temperature jump. There is a large temperature jump at the interface. What that tells me is that the thermal resistance at the interface is much larger than the thermal resistance of the blocks themselves. Which is not surprising, the blocks are made up of copper. Copper has high thermal conductivity, right? So copper is expected to offer very low thermal resistance, which is why the slopes of these curves are so low, right? But on the other hand, there is a significant temperature drop across this interface, which is essentially the thermal resistance offered by this material. Okay, let me go to my sheet for a second. The thermal resistance by definition is delta T over Q double prime. So if I would like to measure the thermal resistance offered by that sheet which I placed between the two blocks, let me go back here. If I want to measure the thermal resistance offered by this purple sheet, then I want to find out the temperature difference across that purple sheet and the heat that flows across that purple sheet. How will I find out the temperature difference across that purple sheet? It is this number, this delta T between the two curves. You see, if that sheet was offering zero resistance, then these two curves would have been a straight continuous curve. But the fact that there is a temperature drop here means that there is some resistance being offered by the sheet that I inserted between the two copper blocks, right? So I can find out delta T from my measurement. What about Q double prime? How do I know how much heat is passing through the sheet? Sure. There are a few ways of doing that. If I measure how much current is passing through my heater and if I have reasonably insulated around it, then the amount of heat passing downwards is equal to the heat that is being generated in the heater device, right? That is not always true because some of that heat may very well leak here and there, right? Similarly, the amount of heat passing through the sheet can also be said to be equal to the amount of heat being removed by the by the water, right? But then again, it is also possible that some heat is coming into the system from here and there, and the two may not be equal to each other. The best way of finding out how much heat passes through this is by using the copper blocks as a reference. How much heat is passing through the copper blocks? At the top, the amount of heat passing through the copper blocks is given by K copper multiplied by dt dx, the slope of this line, right? The heat passing through the bottom copper block is given by K copper multiplied by the derivative of temperature in the bottom block, right? Remember we said very early on, Q equals negative K dt dx. The good thing is the thermal conductivity of copper is well known, and therefore if I multiply K copper by the temperature gradient in both blocks, then that gives me the amount of heat passing through the top and the bottom blocks, and that both of them must be equal to the heat passing through the separator. That was the basic idea in the paper. So having done those calculations, we can find out the resistance offered by this sheet of whatever that sheet is made up of. And then of course, once all of this is ready, I can repeat this as I had said for the cathode alone, then the separator alone, and then the sandwich of both of them. So by 3 experiments, I will have found out our cathode, then our separator, and then our total. And from there it is straightforward for me to find out our cathode separator. Okay? Any questions? We can. So this experiment in which we are doing these measurements, if I take this separator and if I wet it in the electrolyte and put it there, then I can account for the effect of the electrolyte. We had a lot of difficulty doing that. Those were early times. We didn't know how to handle electrolyte and so on, and that electrolyte of course would evaporate and so on. So our measurements were done on a dry sample.
Then there will be the here the thermal resistance which we are calculating. Value must be.
Yes, it must have affected it in some way, but we made the argument that since the thermal conductivity of the electrolyte is so low, it probably does not offer a good heat transfer path for heat to pass through. Okay. Looking back at it, this was certainly a weakness of this paper in that we could not quite measure the thermal properties in the presence of the electrolyte. What would it have needed for us to do it? We would have probably needed to do this in a glove box with saturated electrolyte conditions, which would discourage the electrolyte to evaporate, right? You do it in a dry environment, all the electrolyte will easily evaporate. But if you already have some electrolyte, volatile electrolyte all around this experimental setup, then the electrolyte will not have a reason to evaporate, right? And then we may be able to run these measurements on wet samples.
By creating electrolytes.
Exactly, by creating a high, I wouldn't call it humidity, but high concentration electrolyte vapor in the vicinity of the sample. Yeah, that's a fair point, and we did get some critique of this paper along the same lines, that you're not really measuring the thermal properties in the presence of the electrolyte. Any other questions or comments so far? So let's go look at the results now. So this is sort of schematic of the experiment. Separator alone, and then the entire stack, and then only the cathode side. So 3 sets of experiments that allowed us to take these measurements. Here are the results. I want you to forget about the right side for now. Let's just focus on the left side. So what the left side does is that it talks about the various components of the total thermal resistance of the unit cell that I am considering. Remember, the unit cell comprises the two current collectors, the cathode, separator, and I am ignoring the anode side for certain reasons right now. I'm only focusing on the half cell, the cathode side half cell. And this table lists the measured values of the thermal resistances of each component. We did not bother to measure the thermal resistance of the current collector because they are made up of copper and aluminum. I have all the reason in the world to believe that their thermal resistances are extremely low. So that is why those thermal resistances are less than 1 watt microkelvin meter square per watt. Okay. The cathode offers a little bit of resistance. The separator offers a good deal of resistance, which is expected because the separator is made up of polypropylene, a polymer material, which typically has low thermal conductivity, right? But the majority of thermal resistance, about 88%, we found was coming from the separator cathode interface. So it turns out that the two resistances offered by the materials are sort of like this, and the resistance offered by the interface is sort of like this. This problem is dominated by interfacial resistance. Once the heat gets into the cathode or into the separator, it can get through it very quickly. But then there is a backup at the interface. There's construction going on there, which is why all the cars are lined up and there is a big traffic jam. And now, as a highway engineer, if I want to come in and try to improve the traffic, then where should I put my efforts? Should I put my efforts in the roads which are nice and smooth, or should I put my efforts in the road where there is a lot of potholes or there's construction going on? Clearly, where there is construction going on, right? That is where the heat is having a lot of difficult time in passing through, right? That gave us a hint that look, in order to improve the thermal performance of the cell, there is no point trying to improve either the separator or the cathode. Those roads are pretty nice and smooth already. There is a small patch of road where there's a lot of potholes. That is where I need to go and fill those potholes so that the overall journey for the heat can be as smooth as possible. So around that time, there were papers that were talking about adding carbon nanotubes to the separator in order to improve its thermal conductivity, or adding boron nitride, blah blah blah, to the cathode, etc. We said, folks, stop, there's no point of doing any of that. If in the best case you come up with some separator that has excellent thermal conductivity, you put nanotubes, graphene, whatever is the flavor of the day for carbon materials, you saturate the separator with it. In the best possible case, what will you do? In the best possible case, what will this 100 number become? Resistance 0, right? If you take a lot of effort, that resistance can be brought down all the way to 0. But even then, if this green thing becomes 0, the total thermal resistance still does not change much, right? You've got to put your efforts in the right place, right? You've got to put your efforts in the right place. And here, the thing that requires the most attention is the interface, not the material itself. And this is not uncommon. This is not the first time people saw interfacial dominance like this. In microsystems, when materials are very small, interfacial dominance is quite common, because imagine I have a material that is becoming smaller and smaller and smaller. Once it becomes small enough, then the heat can pass through it very quickly. But the interface continues to offer a problem. Here, the materials themselves are conducting enough, but the interfaces are very poor. And there are reasons behind that. Somebody asked me yesterday or the day before, how is the separator and the cathode put together? Is there some glue between them? Do we put some kind of epoxy between them? No, the answer is no. They are simply stuck together at high pressure. So those four or five sheets that make up the cell, we bring those sheets together. I think there was a picture in the other paper, right? We bring these sheets together and we basically clump them together with some pressure, and then we roll them into a cylindrical cell. We do not do anything to try and adhere them to each other. Why? Because any material that I place between them can hinder the flow of lithium ions. I want lithium ions to pass through in an uninhibited fashion, which discourages me from putting glue between the two, right? But the problem with that is that if you take two materials, no matter how hard you push them into each other, they may or may not adhere to each other in the true sense of the word. Right? If you have one material which is slightly positively charged, the other material which is slightly negatively charged, they will come together very nicely and they will adhere very well, and the heat will be able to transfer from one to the other very nicely. It all depends on the chemical composition of the interface, of the surface. If the two surfaces don't like each other, no matter how much you push them, they will never really intimately connect with each other. And we suspected that that is exactly what was going on here. So then, Ravi and Vivek and I, we asked ourselves, what could we possibly do to enhance this heat transfer problem? We had hypothesized that the poor contact resistance between the two is happening mainly because of poor adherence between the two surfaces. None of us were chemists, but we said, why don't we do something to improve the adherence between the two surfaces? About the same time, another student of mine was running experiments using DNA, and he was trying to take DNA and stick it to a glass slide in order to run some other experiments. And he had learned that in that world, they commonly use certain molecules called aminosilanes in order to stick the DNA to the glass. The idea being that aminosilane molecule has a slightly positive end and a slightly negative end, and therefore the DNA comes and sticks on one side, the glass slide sticks on the other side, and this molecule basically acts like a molecular bridge between the glass slide and the DNA, allowing the DNA to stick to the surface. So we said, okay, in the absence of any other expertise we have about chemistry and all that stuff, why don't we try that out? So we took our cathode, the blue thing, and we placed the aminosilane molecule on it. Okay, we were doing this completely blind. We took a molecule and a experimental recipe that was primarily developed in the world of biology, and we said, okay, let's try it on lithium ion cells. Okay. On the other side, we carried out a plasma treatment of the separator. So just stick it in a plasma, oxygen plasma for 5 minutes. That basically cleans up the surface and provides a slight positive or negative, I forget what, charge on that surface, right? And then we stick them together. So experiment A is the baseline. Experiment B is one in which we only do silane functionalization, C in which we only do separator plasma treatment, and D is in which we do both of them. Because our hypothesis was that when we do both of them, that is when we will get the best effect and we would have reduced the thermal contact resistance. Okay, so we do all of this, we go back to our experimental setup. Remember the one I showed about the 2 copper blocks, and we repeat this measurement. And by now this copper block is getting heavily used, right? We are running a bunch of measurements one after another on this copper block. Remember that every time we run this experiment, we have to flush the water lines, we have to allow this system to reach steady state, and only then take our measurements. So takes a little bit of patience to take these measurements, right? But having done all that, if we compare the results of the baseline experiment with the enhanced experiment, you can see here that the first 3 components of thermal resistance don't change, but the interfacial thermal resistance reduces quite dramatically. It reduces by about 4 times by introduction of that aminosilane molecule between the 2 surfaces. By doing so, I am able to reduce the contact resistance from 840 microkelvin meter square per watt to only 180 microkelvin meter square per watt, because of which the total resistance also comes down quite significantly, right? I'm able to get a significant reduction in the total thermal resistance primarily because I identified the rate limiting step and I focused my energy on reducing the rate limiting step. It is, if I go back to my slides, it is this biggest resistance that I must focus my energy on and not these itty bitty things, right? If I'm trying to save money and if I spend 10 rupees on chai every day and 200 rupees on cake every day, then I should be looking to reduce my cake consumption, not my chai consumption, right? That's what is happening here. Any questions?
How you can claim that using this will not affect performance?
That's a good question. Absolutely. So you see, one good quality of research is that you need to be able to preempt, you need to be able to guess what kinds of questions you will get. Okay, so any reasonably knowledgeable person, when looking at this, what kinds of questions he and she will ask, right? That way you can prepare yourself for those questions coming from your dissertation committee or from your job interview or whatever it is, right? And this is a perfectly reasonable question to ask. I have placed that aminosilane molecule between the separator and the cathode. What is the guarantee that the lithium ions will not be stopped by that aminosilane molecule? Well, we did not know enough chemistry to answer that question. So we said, let us build cells. One cell without the aminosilane molecule, another cell with the aminosilane molecule, and see if their performance is significantly different or not. Okay, and when we do that, the results are in the paper. This is a charge discharge curve and this is an EIS measurements. These are, I have not introduced these in a lot of detail, but these are basically characterization experiments to understand the nature of electrochemical transport in the cell. In other words, how good is this cell from an electrochemical point of view? Okay. I think Dr. Agrawal had referred to some of this in his presentations, right? A lot of the theoretical modeling that he had presented was focused on predicting the discharge curve. So here what we did was that we took these 2 cells that we had built, one with the aminosilane molecule, one without the aminosilane molecule, and then we charged and discharged those cells for a few cycles, for only about 10 cycles if I remember correctly. Okay, and we showed that the baseline experiment and the enhanced experiment had more or less, not identical but more or less the same discharge characteristics. The EIS curves were also not too different from each other. Okay, this does not prove by any means that the aminosilane molecule will absolutely not disrupt the lithium ion transport, especially over a large number of cycles. We do not know. I mean, these experiments were only done for about 10 cycles. In reality, a lithium ion cell is expected to charge and discharge thousands of times. We do not know if that aminosilane molecule will survive, stay there for that long, and therefore we do not know what the effect of the aminosilane molecule will be on the long term thermal and electrochemical performance of the cell. That experiment we did not do. In all honesty, that experiment remains to be done. We in our lab simply did not have the equipment to run cycling over thousands of cycles. That's a field of its own, and we simply were not equipped to do that. So for the purposes of this science-based investigation of a potential technique, we are not looking to solve the problems of the entire world. All we are doing here is to propose one possible technique for solving the heat transfer problem, right? We haven't even implemented it in real lithium ion cells, but there is some proof of concept that quite likely this is probably going to work. Yes.
How you treated them? Did you compare with the commercial cell?
No, this was the baseline here is our own cells without the aminosilane molecule.
You have made it the flat C.
Yes, we made a split flat cell with an active area of the details are here. So we used lithium anodes. We purchased lithium anodes because this was all being done on the cathode side. So the lithium anodes were the same. On the cathode side, we used a baseline cathode separator, and we used one including the aminosilane molecule.
That too without
No. This experiment was done with electrolyte. Of course, we need electrolyte in order to charge and discharge the cell. So this experiment was done in the electrolyte, and we found that the two were nearly the same.
all the fermentary sealing or
Everything was identical, and it was done using a standard process. So Fuxiang Liu, who's one of the authors, was the one who built the cells for us in his lab. He had that capability. So collaborations, folks, are important. For a fairly large project like this, there are multiple aspects of it. Heat transfer, of course, being the central one, but you need somebody with electrochemistry expertise, you need somebody with microscale heat transfer expertise, and we were fortunate to be able to pull a bunch of people together to be able to write a decent paper. Okay. Of course, this does not solve all the problems of the world. Okay, there are several holes here. Why aminosilane? Why not any other molecule in the world? If you go and talk to chemists, then they will say, well, there are different candidates of bridging molecules that you can use to bridge these two materials, and the aminosilane molecule, which we basically pulled out of a hat simply because somebody else in our lab was running some other measurements using the same molecule. We perhaps got lucky because it gave us decent results, but who knows, there is some other molecule that could perform much better than our aminosilane molecule. So I'll address that question as well in another paper in a little bit, but are there any other questions?
there can be some effects at higher temperature on the
Sure, it is quite possible
can be controlled.
that the bonding might deteriorate at higher temperatures. Yes. In some sense, this paper only opens the gate, right? I think a good paper, not saying this is one, but a good paper certainly leaves a lot of questions to answer, right? There is no paper in the world that will answer all the questions. But if there is one paper that says, oh, this is interesting, What about we do this or what about we do that? A good paper is one that opens up new lines of inquiry, right? Motivates you to investigate that this direction and that direction. And certainly in our limited world, this paper in 2014 or 15 certainly played that role, that it allowed us to start asking all kinds of other questions related to heat transfer in the cell. Any other questions or comments here? Yes. Of what is the thermal conductivity of aminosilane? Well, I don't know the bulk thermal conductivity of aminosilane, but keep in mind that here the aminosilane molecule is just a single molecular layer between the two surfaces. It's just one molecular thick layer between the two materials. It does not make sense to talk about the thermal conductivity of a single molecule, right? Thermal conductivity is a bulk property, right? But nevertheless, you have a good point in the sense that in order to understand the role of aminosilane in improving the thermal contact between the two materials, we have to look at what is happening at the scale of atoms and molecules. And that is what another student of mine did a few years later. I'll pull that paper and I'll show that as well. So in other words, we realized at this point that if I want to evaluate multiple candidate molecules in this job of bridging between the two surfaces, say I give you 10 potential molecules and I ask you which one of them will work the best. There are two ways of doing that. One is running all these experiments all over again for each of those molecules. And the other is to evaluate these molecules using simulations. We took the second approach in our work mainly because by then Vivek had graduated and actually a lot of other co-authors on this paper had also sort of scattered away, and it was very difficult for us to rerun these measurements all over again. On the other hand, I myself did not have expertise in simulations, and here I am not talking about the simulations we've learned in our class. Those are continuum simulations. Those simulations apply to relatively large sized bodies, at least tens of microns thick or larger. Whereas what we are interested here is in a single molecular layer of aminosilane between two bodies, right? I need to look at how heat flows through atoms and molecules, not through materials. And the kinds of simulations you need at the scale of atoms and molecules is very different from simulations at the scale of materials, because at the scale of materials the governing equations are Fourier's law, q equals negative k dt dx and so on and so forth, right? Those equations are actually continuum representations of heat transfer at the nanoscale. At the nanoscale, we need to look at what happens to an individual atom as you heat it up. As you heat up an atom, it begins to vibrate faster, because of which it pushes the next atom into vibrating faster, because of which that pushes the next atom into vibrating faster, and that is how heat flows. In order to look at this process at the scale of interest here, at the scale of an individual molecular layer, I need to do simulations that account for individual molecules. We didn't do that in our simulations yesterday, right? We didn't even worry about individual atoms and molecules. We just said, okay, this material has a thermal conductivity of whatever. That number that we assign sort of captures the behavior of atoms and molecules. Atoms and molecules that don't vibrate very fast and don't transfer the vibration very fast have low thermal conductivity. And atoms and molecules that do that transfer very effectively have high thermal conductivity. That is how we account for those atoms and molecules in our bulk simulations. But what we want to do here is to go down to the scale of individual atoms and molecules. Those simulations are called molecular dynamics simulations. MD simulations. Is there anybody here who does molecular dynamics simulations? No, not quite. That's different.
We tried some DFT.
DFT, exactly. Yes, yes.
Tried for some graphene oxide sheets for
Yeah.
absorption of toxological assessments.
Mhm.
So we did it experimentally.
Mhm.
Then we have uploaded the X-ray diffraction data and the chemical kinetics data to examine how effectively the graphene sheet can act as a micro observable filters for pharmaceutical effects.
Sure, absolutely.
So we are trying to monitor.
Yes, and that happens at the scale of individual graphene molecules. You have
Single sheet of
exactly single sheets. Absolutely. So the idea behind molecular dynamics is very simple to very similar to billiards. Snooker.
yes.
Yeah. So atoms and molecules in some way behave similar to billiard balls on a billiards table. Okay. The temperature of any atom or molecule corresponds to its speed. The what's it called? Stick. Sure. If I take a stick and if I hit this ball at a high speed, then this ball will, this process causes a transfer of momentum from this ball to the other ball. This other ball will also then a bunch of these balls which were initially stationary will now begin to move. Right? From a heat transfer point of view, this process is exactly what happens and is responsible for the flow on this side. Right? And this is at a low temperature, but as time passes, the heat flows from the hot side to the cold side. And how predicting how these billiard balls are moving? Sorry? Momentum conservation, exactly. If I have a ball, if I have two balls that are traveling, they come and hit each other and move their own ways. A1, B1, A2, B2. One refers to before, two refers to after. Then the total momentum must be conserved, right? So momentum of A coming in plus momentum of B coming in, and these are vectors, must be equal to the momentums of A and B added together, right? I can apply this very simple principle on billiard balls. I can also apply this very similar principle on individual atoms and molecules, and I can see how they will travel around and they will transfer heat from one side to the other. That, in my limited, crude knowledge of molecular dynamics, is all that there is to it. Molecular dynamics, however, is much deeper. Okay, and I've only given you like I mean, I'm sure an expert can take a whole Gyan course on molecular dynamics simulations and more, right? Myself not being an expert, I sat on this problem for quite a while and actually talked to quite a few potential collaborators, and things quite did not work out. Okay?
Because every tool will be having a different significance.
Yes.
It cannot predict that it cannot able to execute. We have tried about 2 to 3 tools that we have optimized the conditions.
Yes.
Anyways, ours is a different set of applications.
Correct.
That is, but we are into different set of
Right.
the denudation efficiency and the computation. So we tried more than 6 to 8 months for different tools.
Correct.
Gaussian we tried, secant we tried,
Yes.
and finally we tried with another version of Gaussian.
Yes.
And it requires a supercomputer.
Yes.
Not with ordinary laptop.
Yep, absolutely. So there you go. There are challenges in doing this, and how we overcome these challenges is a funny story. So I was spending a summer at the Air Force Research Lab in the US, and I had enrolled my little kid. He was, I think, 2 or 3 years old at that time, at a daycare there. I was dropping off my kid at the daycare where I saw a familiar face, and I couldn't quite figure out who that guy was. But he was dropping his kid there every day. In a couple of days, we figured out who he was. He was 1 year junior to me at IIT Delhi. Do you remember uh, Vikas Varshni, electrical engineering department, 1 year junior to us? 1 year junior to us. Biswadeep Bose, his group, his year, Biswadeep Bose's year. So I happened to run into him out of the blue in some unfamiliar place, and we were of course extremely happy to see each other. And we met, families met, etc. We are still very good friends and all that. And then we started talking about what we do, right? And it turns out that he is a good expert in molecular dynamics simulations. So I went to him and said, Vikas, we've got to work on this. We've got to figure out how to solve this problem. I really want to. And he said, yeah, of course, I'm happy to help, and so on. And one thing led to another. I'll show you that paper. This was in 2015. The paper with Vikas was much later. As I said, I sat on it for a long time, and then the work itself took a little bit of time to happen. What am I looking for? I'm looking for Dhakane. There. So that happened in 2020. Remember, the goal was for us to somehow get a confirmation of the experimental measurements. Experiment said that if you put an aminosilane molecule, the contact resistance will improve. So I wanted to confirm that through simulations, and as a bonus, I also wanted to be able to carry out a comparison between different materials, material A, material B, material C, which one of them offers the best contact resistance between the samples. Who are the students here? Abhijit Dhakane was at that time a master's student in my lab. He left after his master's and he joined Oak Ridge National Labs for his PhD, and he is now about to finish his PhD. And of course there's Vikas, and there's a couple of other people who Vikas introduced me to. So he said, you know what, we need another expert to work on this part of the problem. So he talked to his friends, and we all got together and did this work. And I'll show you, the idea is very simple, and it is very similar to the experiments that we had done. In all honesty, I don't know more than 10% of this paper myself, because it was all done by other experts. And Abhijit, the lead student, to give credit to him, he was able to learn a bunch of these things, a bunch of these simulation techniques, talking to Vikas, and he was able to lead this work. So in some sense, I was just the facilitator. I just got all the people together on the same table, and then they all got talking. I'll show you. Yep. So this is the molecular dynamics simulation that we had done. We placed individual molecules of lithium cobalt oxide on one side, which is the cathode, amorphous polyethylene on one side, which is the anode, sorry, the separator, right? And we placed a very thin layer of, actually there is no, this is without the bridging molecule, there is nothing in between, the two are touching each other directly. And I think if I go further down, I now have a thin layer of the aminosilane molecule between the two. Okay, I will perturb this system from the right. So from here, I will assign a high temperature. I will basically take the stick, the billiards stick, and I will hit all these molecules and I will force them to start moving very fast. And they will transfer their energy to the next ones, to the next ones, and so on. And that heat will pass through the aminosilane molecule layer and go into the polyethylene. This is sort of like playing billiards with molecules, and this is very similar to the experiment that we had done. In principle, the experiment and the simulation, they both are doing the same thing. Yes?
There, where you are, in the experiment also there you are using the lithium cobalt.
Correct. Yes. Yeah. Actually, I don't remember. I'll have to go and confirm. Maybe there was a slightly different chemistry there. And the reason why we chose lithium cobalt oxide here was that these simulations need the, I think they're called the force fields, the force potentials or something like that. And those we were able to only find for lithium cobalt oxide, not the other molecules.
Properties required or the variables required for the experiment.
Yes, the variables required here are not thermal conductivity, heat capacity, density, etc. Those are bulk values. The properties needed here are the intermolecular potential force field, Lennard-Jones force field, something like that, of these molecules. You can see I'm not an expert here, but you know, if you don't know something, what do? You go and talk to people who know. And if one of them turns out to be your batchmate, that really helps. Yes. No, electron mobility is not considered here. There is no flow of electrons here. Hmm. Yes, in general, heat is transferred by both electrons and phonons, but here the contribution of electrons is zero because polyethylene and lithium cobalt oxide are both insulators. They don't, you can't pass current through polyethylene. Yes. हाँ 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 I should have said that. So the billiard ball example that I showed was not in the case of a gas, they are the atoms themselves. Gas के atoms तो travel करेंगे here and there. Solid के atoms don't travel here and there, and therefore the balls that I showed there are not the atoms themselves, but they are the vibrations of those atoms. In fact, those vibrations are called phonons. Lattice vibrations, exactly. वो जो lattice vibration होती है, that is the one that travels. कि आपने इसको vibrate किया, उससे कारण ये vibrate हुआ, उससे कारण तीसरा vibrate हुआ, तो आपकी जो vibration है वो travel कर रही है. And so you imagine as if those vibrations are represented by a particle, an imaginary particle. That imaginary particle is called a phonon. So when that vibration travels, we imagine as if there is a particle called a phonon which is actually traveling. Okay? Any other questions here? So once Abhijit was able to do the baseline simulation without anything in between, and then he was able to do the simulation with the molecular layer in between, then he said, okay, let me go on a hunt for different bridging molecules and see if I can implement each one of them in my simulations. These are fairly time consuming simulations as you had indicated, right? Our ANSYS simulations yesterday finished within a few minutes. This setting it up takes several days. I see you smiling, and the computational cost of this is not measured in terms of few minutes on a laptop, right? This is several hours on a supercomputer sort of a deal, because we are talking about individual atoms and molecules moving around and solving those complicated equations. Okay, this by itself, by the way, is a very rich field. I just don't have that expertise, but you know, there are people who have built careers out of molecular dynamics simulations for a wide variety of different applications, not just heat transfer. So I think these are the three molecules that he had he had considered, and you can see that a lot of these plots are very similar, and the whole flow is very similar to the experiments, right? We take two materials, stick them next to each other, heat up one side, cool down the other side, do this measurement of temperature versus X, and find out this delta T, right? The simulations and the measurements are walking along similar lines. And when he did that, let me get to the right plot here. I guess we can look at this. He shows that compared to baseline, if you have 10 layers, 20 layers or 30 layers of aptase molecule, which is that aminosilient that I keep talking about, the thermal conductance, sorry, we need to flip our thinking. He's plotting conductance, not resistance. So do I want the conductance to go up or go down? I want it to go up, right? Sorry about this. We really should have. I think this community talks about conductance rather than resistance. So the baseline conductance was about 100, and then when he started adding these aptase molecules, it jumps up to about 300 or even 400 megawatt per meter square per Kelvin. So in principle, the improvement that our experiments showed are also seen in molecular dynamics simulations. Here, the best possible improvement was about 250% with the APTS molecule. He tried it with another molecule and he found that, yeah, there is some improvement, but it's not great. So he has effectively developed a tool which can evaluate and compare the performance of different molecules before you even take the effort of purchasing these molecules, setting up your experiment, running those measurements, taking the data, analyzing it, etc. Before you do any of that, you can run this simulation, and the simulation is able to help you say, you know what, don't even worry about that molecule. It's probably not going to work. But these two molecules which are showing good promise in my simulations are the ones that we should probably focus on. Right? None of these simulations capture all the real physics of the problem. The real problem is much more complicated. It has binders, the surfaces are rough, all kinds of real world considerations exist in the real thing, right? This, all of this, the experiment, the simulation as well, both of these are idealizations, approximations, but nevertheless, at the very least, these point us in the right direction. These tell us no point looking at this molecule. You've got to focus on the APTS molecule. And this one is actually very poor. In this one, the improvement is, there's hardly any improvement. In fact, it might even get worse. And so, from this we concluded that one specific molecule is the one that we should be focusing on. This paper, I think, has gotten quite a lot of traction. There are other papers that have built upon this work, molecular dynamics, to understand the molecular bridging between materials for lithium-ion cells. I know there's at least one more paper in which they presented how hydrogen bonding between the two surfaces can help improve thermal transport between the two. And of course, you know, going back to one question that you raised, this is a purely thermal simulation. This does not address how the transport of lithium ions will be affected by the presence of that molecular layer.
Even electromagnetic, those
Are also not present here, yes. God knows this problem is already complicated with 3 molecules, adding another one and motion, right? And the transport of lithium ions, which is probably governed by a different set of equations, will probably make this simulation quite complicated. But you know, I suspect that if a PhD student takes this up from start to finish, this would make for a very beautiful PhD dissertation, right? It's a difficult problem, but give enough hard work for a few years I think it can be solved. Okay, all right. We are almost done with our time here. Is there anything else that I want to say here? No, I think I think I covered most of the stuff that I wanted to. So let's take a break, and after the break, Dr. Chandrasekhar Sharma will give a seminar on his perspective on thermal management of batteries and other devices. All right. So let's be back in an hour. This time is